Hi guys, hope you're doing good. This is the first video in a series of lectures covering the Laplace transform. We're going to be looking at this from an electron engineering standpoint. So instead of dealing with purely functions, purely, different expressions, we're going to look at this from the standpoint of RC circuits, RLC circuits, and how the Laplace transform helps us to solve that. So this first video is, what the Laplace transform actually is. We're not going to do any mathematics here, just to get ourselves familiar with the theory at hand. So let's get to work. Why does the Laplace transform exist? Obviously it's named after this founder, Pierre-Simon Laplace, a French mathematician, physicist, scientist, engineer guy. So what actually happened was that he was dealing with probability functions, and he just said, all right, what happened if you take the integral? Probability and generating functions actually. So at the end of the day, they ended up taking the integral of e to the minus st dt. This is a simplification of the history, but essentially it's a bit more complex than that. But essentially what they found out was that once they did this, you were able to analyze your function from an entirely different point of view. You're taking it outside time and you're looking at it from a complex plane. So what this means is that it's able to transform ordinary differential equations to purely algebra. So where you may have, let's say f double prime of x plus 3 f of x minus 2, right? This is a differential equation, and to solve this, assume a solution, you find your coefficients, etc., integrate. So lots of mathematics. But once you apply this Laplace transform, it changes this from the complex differential equation all the way to simple algebra, where you have nothing but plus, minus, and a fraction, right? And that algebra is going to be dealing with the complex variable s. We'll get more into this, in the later parts of this video, actually. So this function is to be able to analyze things in the complex domain. Naturally, we deal with things in the time domain, okay? But with the Laplace transform, we move it to the complex domain, usually call it the S domain. We'll explain this as we go on. And the main reason this even works for electrical engineering is because of Oliver Heaviside. That's a funny name. So Heaviside is actually has a lot to do in EE actually, because he's the same guy responsible for transmission line and coaxial cables and the mathematics for that. So he's the one that said, all right, this function that Laplace has been used for probability, and since we have differential equations when dealing with capacitors and inductors, why don't we use this to model solutions for electro engineering circuits? And that was what he was able to do. So let's move on. The time domain versus the S domain. Remember what we said, that the purpose of the Laplace transform is to move things from the time domain, where, voltage is a function of time. If you were to draw your VT graph, you call this voltage, you call this time, and then let's say, it decays over time. Simple. If you were to draw this is crooked. If you were to draw your current time relation, this may be current, this may be time, and let's say starts low, then which is a peak value. These are the way we are accustomed to analyzing circuits over time with time as our variable. So you have V as a function of t, you have I as a function of t, and then you deal with differentials here, because for capacitor current, I of c is c dv dt, all right, and inductor voltage is L di dt. So these are naturally, since you're analyzing in the time domain, we will become used to dealing with derivatives of voltage and of time. But what happens when you come over to the S domain is that all this becomes algebra. That's what this diagram. This is a try to picture it. This is to help us picture what happens when we move from the time domain to the frequency domain. So what used to be your V as a function of time? I say this is your voltage as a function of time. This is a bit clearer. So this is time, and this is the S domain. What used to be voltage as a function of time? Okay, this is small letter. What used to be voltage as a function of time is now going to be capital V as a function of S. What used to be current as a function of time is going to be capital I as a function of s, and that's the transformation that happens that makes solving RLC equations easier. And what used to be derivatives, right? Let's say we have d over dt, is just going to become plainly s. So taking the derivative of something in the time domain, you will usually have d dt, d squared dt squared, d cubed dt cubed, okay? It's just s squared, s cubed, which is simple algebra. And the same thing as taking an integral, or usually be an integral in the time domain, is the same as dividing by s, the complex function. So what the Laplace transform does, as we've said, is that it takes a function. Let's say we have a resistor. Let's call this time. I have a resistor R. I have a resistor here. So let this be T for time. Ooh, okay, that looks like tau. This for time and this for S, right? You have R in the time domain, and then you have R in the S domain. But when you deal with, complex elements like capacitors and inductors, okay, let's do with inductors. An inductor will have a value of L in the time domain, right? Inductance L. The voltage across the inductor is going to be L di dt. But if you transform it, you're dealing with functions of time, moving its functions of S. If you transform it to S, you're going to end up with SL. Okay, S is a complex variable times L. All right, same thing, an almost identical thing for capacitors. Capacitors is capacitance C, current IC is C dB dt, and then you just end up with a simple 1 over SC, which makes the mathematics much more simpler. All right, so you move real variables to complex variables. Now this S is, sometimes you call S domain the frequency domain. So you might see S or frequency domain. Oh, pardon my handwriting. Oof. Let me see if I can tidy it out. S or free UENCY. S or the frequency domain. What does that mean? All right, S is a complex. J, J is the complex number for us in EIE. So J means, once you see J, guys, we're dealing with complex numbers. This omega now is our angular frequency. So once this angular frequency is here, you know that you're dealing with things that are oscillating. All right, sine functions are oscillatory, cos functions are oscillatory. Now this sigma is the real part. And what this does, if your sigma is greater than 0, that means you have a growth. Okay, so you have an oscillatory growth. If it's less than 0, if it's less than 0, then you have a decay. Oscillatory decay. Oscillatory and exponential at the same time. So that's what S is. So it helps us to know, all right, we have a periodic function. That's the point of the J omega. That's the complex times the frequency. And then is either going to either grow or decay. Because since we're dealing with this kind of elements, their parameters won't stay the same forever. You get? All right. So wrapping up, why it works for circuits, that's exactly what we just explained before. It transforms from SL, it transforms from the time domain to the frequency domain. But resistors stay the same. So resistor or resistance R in the time domain, let's call this F for frequency, is going to be the same as R in the frequency domain. All right. But then with inductors and capacitors, this SL and 1 over SC becomes their impedances. All right. So to find the voltage, let's just do a little, I didn't plan to do this. Let's do a little tease. So this is L in the irregular time domain, and then we're going to have SL in the frequency domain. So usually in the time domain, you won't bother yourself with the impedance, with the resistance of an inductor. But here, since you know that SL is the resistance, voltage, if you were to find the voltage across the inductor, this time as a function of S, it will now just be current times SL. All right. Whereas if you were to do it here, VL as a function of time would be L di dt. So you can see this is a differential equation. This is a differential equation, and this is an algebraic equation. That is exactly the beauty of the Laplace transform. it's related to the Fourier transform, etc., etc. But we'll get into that in later videos. This is just to understand, to get a background of what happens. So we are trying to go from complex mathematics, complex differentiation, complex integration, right? So where you have d over dt, you have a multiplication by s, all right? Where you have an integration, we have a division by s. This is what we're trying to do when we work with the Laplace transform to make RLC circuits easier to solve. All right, so in the next videos, we're going to get into more mathematical expressions, get into derivations of all of this, then, bring up circuits and solve problems.